Welcome back to today's lesson. So we are on Unit 1, Rates of Change, Lesson 5. Today we're going to talk about limits and continuity. For most examples to this point, you have used a graph to determine the limit. While the graph of function is very useful for determining a limit, it is also possible to determine the limit algebraically. The limit properties presented in the table can be used to calculate the limit without reference to a graph. A few of these properties are intuitive or a little bit obvious. Now, for instance, the first two, the limit of a constant is of course a constant. The limit as x approaches a is equal to the function a. The limit of a sum is the sum of the limits. The limit of a difference is the difference of limits. Now, if you have a limit of a function that has a constant out front, then you can simply pull that constant out front and take the limit of just the function. We'll take a look at this a little bit further. Some of these will become obvious and you'll get used to using them. Let's take a look at example number 1. Example number 1 asks us to evaluate each limit if it exists. Let's first take a look at a. A is the limit of the function 5, or constant 5, where x approaches -1. In a, what that means is no matter what value of x you have, the function is always 5. So in the case of a, the limit is 5. Okay, so let's take a look at b. b asks us to evaluate a limit 3x to the exponent of 4 minus 5x as x approaches 2. So remember that the limit of a smooth continuous function as x approaches a certain number is simply the function evaluated at that number of x. So the easiest way to do this, let's write this down here. So is equal to, what you're going to do is simply replace x with the value of 2. Like so, okay, and then evaluate it. So our answer is simply 38. Okay, so our limit is 38. Let's take a look at part C. Part C asks for the limit as the square root of 2x plus 5 as x approaches -3. So we're going to do the same thing. Let's take C here. There we go. So I'm just going to write down. Again, I'm going to write out the function and I'm just going to replace the x with the -3 and then evaluate it. These are more straightforward ones. We're going to take a look at ones that are limits that are a little bit more complicated, but for now, let's just do this. Okay. This makes it nice and simple for you to work out. And the answer is -1. Square root of -1. Now, have you tried that in your calculator? Has anybody ever tried that in their calculator? You'll get an error, okay, because it does not exist. Now, the square root of -1 is something called a complex number, which hopefully most of you won't have to encounter when you get to university. But there's an entire number system that is built around the complex number. But for now, in high school, we will not be looking at that. So if you do see something that is a negative sign underneath the square root, remember, we can simply say it is not real. It's not part of the real number system and does not exist. So the limit does not exist. Okay? Moving along to part D. If we look at D, now we're going to do the exact same thing again. I know. You're saying this is too easy. Well, don't get too comfortable. Okay, so I'm just going to replace x with -1 and then evaluate it. So what that gives me is negative 3, okay, and then 4. Okay, so that is our limit for part D. Okay, let's just continue on with part E over here. Hopefully that's not too messy for you. Again, we're going to do the same thing. Okay. Thought I would change the ink so it looks a little bit easier to read. Here we're going to do the same. We're going to replace x with 0. Okay. So what that gives us is negative 3 and then 2. Okay. And our evaluated limit then is just 6. Okay. To a minus. Okay, so let's try and use the same method that we did before, where we just replace x with whatever the number x approaches. So in this case it's 2. Okay. So that gives me 10 over 0. Okay. When I get something like this, I get a 0. What I'll often do is I'll go back and I'll take a look at the function to see if there's anything that I could have done in order to simplify. We'll go through steps on how to do that further on in the lesson. But for now, I'm just going to take a peek. Okay, no, it doesn't look like there's anything I could have done in order to simplify or maybe cancel out some terms. So this is what we get. Okay, so we have a division by a 0. Well, a division by a 0, any fraction that has a 0 over it, is undefined. So that it is undefined, the function is undefined at x is equal to 2, which means that the limit does not exist. So we can simply just write does not exist and move on. Okay. Up until this point, we've looked at smooth and continuous functions. But there are also other functions that are discontinuous. One of such functions is called a piecewise function. A piecewise function, as you can see in this example, is a function that is made of pieces of 2 or more functions, each corresponding to a specific interval within the entire domain. Notice the breaks in the graph of this function. This particular function is called a step function because the horizontal line segments on its graph resemble a set of steps. Notice the holes, the hollow holes, represents that we do not include that number in the function. These filled in dots means that it includes that value. So as we can see, let's take a look at the first step. Okay, the first step, okay, from when x is 0 to when x is 20, a hollow hole means that it does not include 0, but a filled in hole means that it does include 0 or 20. Okay. Studying piecewise functions will help us understand continuity and discontinuities of functions. And we're going to take a look at them a little bit further in further examples. I just wanted to show you this one as more of a visual and an introduction to piecewise functions. Okay, let's take a look at this example. This is an example of a piecewise function. Not only are you given the graphical interpretation of the function, but you are also given the functional or equation form of the function. So you'll always see it like this. Okay, so you'll have the function symbol and then you'll have each section and for what values of x do each of those functions represent. Okay, so what we can see here is that the first part of the function represents somewhat of a quadratic here, okay, and then it jumps to a point, a single point, and then we have a straight line. So there's 3 sections to this piecewise function. A part, state the domain of the function. Upon observation, the function is defined for all values of x. So the domain for x is all real numbers, or we can simply represent this as x ER. And that just represents it. X belongs to the set of all real numbers. Okay. B, we want to evaluate each of the following parts. Okay, so let's take a look at B. B will go I. Okay, so the limit of f at x as x approaches 1 from the negative or from the positive direction. Okay, so it's a positive direction. So if we take a look, where is x? Okay, so there it is right there. So I've gone ahead and highlighted where x is equal to 1. Okay, so from the right side, okay, the graph of the function to the right of 1 is represented by a straight line. Okay, so it's going to be represented by this part of the piecewise function right. We can always just look at the graph as well. As x approaches 1 from the positive direction, the function will approach 2, positive 2. Or we can actually test the numbers in this part of the function right there. So let's do that. I just want to show you two different ways to do it. So we have is this line, which I'm going to replace the value of x with 1. Okay, and then just evaluate it. So as you can see, the limit of the function from when x approaches 1 from the positive direction is 2. Looking at I now. Okay. Let's first just observe the graph, and we'll just do this graphically. Okay, so from the negative direction, we can see that it approaches the value of a half. Okay, you can see that that's about a half right there. Or let's evaluate the limit. So from the negative, when x is smaller than 1, it would be this part of the piecewise function right there. Okay, so for that parabola part. So we'll just replace x with 1 and then evaluate it, which is equal to a half. Good. Okay. So let's go on to part 3. Okay. So the limit of the function as x approaches what? Think back to lesson 4. So remember that the limit as x approaches the number for a function to exist, the limit from the left and the right hand side have to exist and they have to be equal. Well, in this case, they do exist from the left and the right hand side of 1. However, they are not equal. So that means the limit as x approaches 1 for the function f at x does not exist. Okay. All right, let's just write 4 right down here. Okay. So f when x is equal to 1. Okay. What do you think that is? Well, that's just simply equal to negative 2. Just because the limit does not exist does not mean that the function does not exist there. So the function exists there, however, the limit does not. So it means that it does not actually approach a certain number. It just is simply negative 2. Example number 3. Okay, so let's observe the graph. Let's take a look at the graph, and as you can see, it is a rational function. Okay, it has an asymptote at 4, and over here you have the function in equation form. A, state the domain of the function. So the function exists everywhere except for where there's an asymptote. Okay, so number A, just right up here, say x belongs to a set of real number. And you always want to do these squiggly lines such that x does not equal 4. okay? And that's how you would probably represent that, okay? So squiggly lines, x belongs to a set of real numbers such that x does not equal to 4. Okay, so let's take a look at bi, okay? So the limit of this function as x approaches 4 from the positive direction, so from the right side. So let's see what happens. We can even just take a look at this graphically. Okay, so as we increase our x values towards 4, our function actually goes to infinity. So we can even just say this. So we know that infinity is not defined, which means that the limit does not exist. Does not exist. Okay. Let's look at I. Okay, so from the, oh, I think one of these should be negative. I'm just going to go ahead and fix that right there. So the function as x approaches 4 from the negative direction. Okay, so let's take a look at the function. As we go towards 4 from the negative direction, what do we have? The function approaches negative infinity. Okay, and again, negative infinity is similar to infinity in which that it does not exist. It's just that the number gets more and more negative. Okay, so both of these do not exist. So looking at part 3, that means the limit also does not exist. It's getting easy, isn't it? And who said calculus was hard? Okay, so part 4. The function at 4. So when x is equal to 4, well, we know it's an asymptote there, so the function actually does not exist there. So this is a case where not only do the limits not exist, but the function itself does not exist. Looking at this example, we want to evaluate each of these limits if it exists. Now, it is important for us to look at these sort of harder type of limits in which we will have to do a little bit of work in order to evaluate. Okay, so let's take a look at each of these. So A part, okay, so let's examine this a little bit further. Okay, we have a limit of what looks to be a quadratic that is divided by another quadratic. Okay, so if we were to actually put the value of x is equal to 1 into each of these, okay, we would realize that we would get a 0. But whenever I see a quadratic, I always want to factor it. That's just me. Okay, so when you see something like this, if you can factor it, I always look to see if I can factor whether it be a constant, whether it just be a variable from all the terms, or if it's a quadratic. If it's a quadratic, I always try and factor to see if there's anything that I can cancel out. So let's look at A. So I'm going to assume that you know how to factor. But if you don't remember, then you've got a little bit of reviewing to do. And I can always give you more work in that area if you'd like. Okay, so since we're not evaluating quite yet, we're just going to rewrite the limit as x approaches 1. Okay, so we're going to factor the numerator. It's a simple trinomial, so I'm just going to split it up into 2 brackets. What multiplies to 5 and adds to negative 6. So x minus 1, x minus 5. Okay. Do the same thing with the denominator. X minus 2, and x minus 1. Okay, so look, these two terms cancel out, or 2 brackets cancel out, and then I just want to rewrite it again because it helps me to keep track of what I've canceled and what I'm left with. Okay. All right, so now I can evaluate the limit. It's 1 minus 5 all over 1 minus 2. And I'm just going to write it right here, which is not proper form, but I'm running out of room. Hopefully you won't do this. Minus 4 minus 1, which is equal to 4. So our limit is 4. Even though originally when we looked at this, we thought, oh, it's going to be 0. Okay, both the numerator and the denominator is going to be 0. But after doing a little bit of algebra, we come up with 4. So although at the beginning of the lesson when we looked at simple examples where we didn't have to do any work in order to evaluate the limit, always check. Always check to see if you can simplify or factor, or if there's something that you could do. Looking at B now. Okay. So at first glance, what we're going to end up with is undefined. So we're not going to actually have a limit. It's not going to exist. But when I look at this, what I see is a radical, okay? And it's a 2-term radical expression. So when I see those, I always want to rationalize. And I know what you're saying. You always want to rationalize the denominator. Well, in this case, we're going to go backwards. We're going to actually create a radical in the denominator in order to get this x from the denominator. Okay, so we can always do anything anything to manipulate the function in order to get a function that we can work with. Okay, so let's see. Again, I'm just going to rewrite this as the limit approaches 0. Okay. And again, I'm going to multiply it by its complex conjugate. Not complex conjugate, its conjugate. We're not dealing with complex numbers. Which is a +2. Okay. And again, the same here. Okay, so I just sort of sped ahead and did a little bit of the work for you. Multiplying these two radicals will eliminate the square root. Okay, and then it's just -4. As you can see, the positive 4 and the negative 4s will cancel out. And then I'm just going to rewrite what you're left with. Okay, and this is what you're left with. Notice I've kept the brackets because that x is being multiplied to everything. Now that is a plus there. Okay, and then as we can see, we can cancel out the x's. Okay, that eliminates the x from the denominator. Then we're simply left with 1 over the square root of 4 plus x. I realize I forgot the limit, so I just rewrote this. The limit as x approaches 0, so we're left with 1 because we've canceled one of the x's, divided by the square root of 4 plus x plus 2. Okay, so let's now evaluate the limit. So it's 1 over, and we've got the square root of 4 plus 0 plus 2. Okay, and that just leaves us with 2 right here because we have the square root of 4, so that'll be 2, so it's 1 over 4. So your answer for that, or your evaluated limit, is 1 over 4. So in C, okay, we'll notice the same thing again. We will not be able to evaluate it straight up, okay, because if we put this in, we're going to get a 0 in the denominator. Okay, let's take a look at it to see if there's anything else that we can do in order to simplify it. What I noticed here in the numerator, okay, so if we were to replace 1 plus x with just one variable, you'll see that it's a square separated by a negative sign and then yet another square, okay, for the second term. That to me is a difference of squares. So if I see a difference of squares, I immediately want to factor it. Okay, so let's just do that. So all I've done here is expanded the numerator, okay, and remember it's a difference of squares, so we've got both the terms, okay, and there should be a little bracket here, separated by a negative sign, and then over here the second part is positive. Okay, so remember difference of squares. Okay, so now I'm going to simplify a little bit further. Okay, so in the numerator what we're left with is x minus 3, okay, for the first bracket, and then we have x plus 5 second bracket, Okay. Is there anything that we can... Doesn't look like we can actually cancel anything out. So in this case, when we evaluate it, we're still going to get a 0 in the denominator. So it does not exist. Oh well, at least we tried. We only have one more order of business before we conclude our lesson for today, and that is to check your learning. Okay. So does the following graph represent a function that satisfies the following conditions? Okay, so here's our graph right there. So f at 0 is equal to -2, and the limit of the function as x approaches 0 is equal to 4. Make your decision. And the answer is B. Oops. The answer is B, no. Okay, so the function at 0 is equal to -2. However, the limit of the function as x approaches 0 is not equal to -4. And that concludes our lesson for today, and we'll see you next time.